Good morning to everybody, and welcome to the Industrial Ecology Day, and welcome to our session, Advancing Life Cycle Assessment by Integrating Socio-Technical Complexity through Agent-Based Modeling. My name is Gustavo Larrea Gallegos. I am a researcher at the Luxembourg Institute of Science and Technology, and I will be your moderator today. So this session is organized by the Life Cycle Thinking for Complex Systems initiative, and today we'll have a series of presentations that aim to demystify some concepts and provide some guidance in the use of complexity-oriented approaches, more specifically agent-based modeling, when it's combined with a life cycle perspective. Next one, please. So for this, the doctoral candidate, Agnese Fortes, will start with a presentation about the initiative and the motivations, and this will be followed by an introduction to complexity that was prepared by Jonathan Cohen. Then Casper Lang will present how agent-based modeling can be coupled with different flavors of lifecycle assessment, to then finalize with a presentation from Ryu Koide on how agent-based modeling can help in shifting the paradigm in which lifecycle thinking studies are conducted. So we prepare an interactive questioning WooClub to interact with the audience during this hour. So if you have questions, you can put it in the chat, and we'll start discussions at the end of all the presentations. So I now invite Agnese Fortes. She's a doctoral candidate at Leiden University and the National Institute of Public Health and Environment in the Netherlands. So Agnese, the floor is yours.
Thank you. I didn't realize I was muted. Thank you for the introduction. I am gonna briefly present the Lifecycle Thinking for Complex System initiative and give you some practical information. So the initiative originated a couple of years ago when a few researchers, actually some of our speakers today, met at a conference and realized that they shared but a research focus, and also we're facing similar methodological challenges. This shared focus was the intersection of three different areas. Life cycle thinking for sustainability. So we are talking about tools like life cycle assessment, input-output, complexity-driven methodologies, like agent-based modeling or other simulation methods, and complex systems themselves. They were interested in socio-technical systems, technological networks. Although many researchers work across these areas, there was no common platform to bring all of these three together. And this is where the initiative comes in to promote the use of complexity-oriented methods in combination with lifecycle thinking approaches. To provide a platform for people working at this intersection of topics, create opportunities for networking, for research collaboration, methodological development, and encourage exchanges across different domains, because the application areas are very diverse. People involved in the initiative work in circular economy, industrial symbiosis, agriculture, food system, energy, and many more domains. Now to the more practical information. As part of this meeting, you all were invited to join our newsletter. And if you signed up, that means that you will be informed about all upcoming activities and events. But the email address that you see here on the slide is also a way for you to contribute. You can share any relevant events, job opportunities, idea, or anything that might be interesting for the whole community. There is also a website where you can read more about the initiative. You can follow updates and you can find resources. In particular, if you're just getting started in this field, there is a section with recommended literature. You can find recommended softwares, links to online lectures, to summer schools, and so on. And here you can see that already in the past, quite a few activities have already happened. A launching webinar was held in July 2024. Last year, Industrial Ecology Day, there was also a session that was organized. We had a special session at the Social Simulation Conference in Delft, and a paper is being co-authored by actually several of today's speakers, and you will hear some of these ideas later in the presentation. Looking at the future, we have a few ideas. We would like to have more special sessions and conferences. We would like to develop co-develop platforms to potentially add some regular online coffee breaks or discussions to keep everyone engaged. If this sounds interesting to you and you would like to contribute in any way, big or small, we are hosting a working session on the 5th of December at 10 a.m. And you will receive an email invitation soon for this meeting. But if you're interested but not available at that time, then you can reach out using the email address on the slide. We still would like to involve you. So thank you for listening to me, and we hope to see some of you at the meeting.
Thank you very much, Agnese. Thank you for this introduction. To continue, I would like to invite now to Jonathan Cohen. Jonathan Cohen is a researcher at Chalmers University in Sweden, and he's going to give us a brief introduction of complexity. So, Jonathan, the floor is yours.
Yes. So Gustavo, you should be seeing my screen, right?
All good. You're all good. Yeah.
Yeah. So yeah, during my presentation, I will be introducing a bit what do we mean by complexity, and how this complexity could be to some extent tamed by agent-based modeling and our complexities models. As Agnes was saying, our point of departure is our belief that since industrial ecology is examining behaviors of complex socio-technical systems, which are embedded in environmental and institutional context, this is of highly complexity, and recognizing this complexity is critical as sustainability emerges from interactions between technologies, human behavior, resources flows, and regulatory frameworks. In complex systems, we say that the environment, the institutional frameworks, production and consumption systems, they are all part of these socio-technical systems because they share technologies and we are embedded in these systems. And because these systems are usually adapting and changing, we usually talk about complex adapted systems. And that's what makes things complex. So before we start jumping in, we would like you to invite you to our WOOC lab to start understanding a bit more which is your field of application, what are the topics that you work with in the context of sustainability. This information will help us to understand what is the topics that you're interested in, what you're working in, and eventually how we can apply and to share standards and knowledge through for looking at different case studies. So please, if you want to jump in and provide some insights, would be nice to understand where are we all working. And Casper, if you want, I guess you are at the moment looking at WOOC Lab, so whenever you want to share, you can take over. Also, we will continue in this WOOC Lab link and site. So if you want, don't get out of there because the follow-up questions will continue and the interactive session will continue here.
We also share the link to WOOC Lab in the chat if you are unable to use the QR code.
Do you need to
you have to launch the
initialize?
questions. Yeah.
Wait a little bit more because perhaps people want to still join. We now have not everyone in the WOOC lab yet. Yeah, so you get a message to wait for the first question. So I will now go to the first question, and if you still want to join, you can look in the chat. There is a link to the WOOC lab. And if you feel like you already see your topic, you can also like it, so it will automatically be more focused on.
Yeah. Okay.
So we see a lot of interest in circular economy, life cycle assessment, waste management, sustainability, transformation even. You can still enter your answers.
Yeah, I feel that we're covering quite a broad
Yeah,
topic, and dietary
interesting.
shifts, bio-based economy, renewables. Yeah.
So as long as you're in the WOOC lab, you can still answer the questions. Jonathan, perhaps you can
Yeah, I can take
take
over.
it over.
Yes. Thank Casper. Yes, so this is very helpful for us and important to continue our conversations. And it seems like to some extent a lot of us in the audience are working with or engaging to some extent with complexity. Maybe some of us are already developing agent-based models or are thinking about or are curious about how these frameworks could help you in your research or policy analysis. So we usually talk about two main opposing views when we start to develop our models. That's one is about problems that are complicated, such as launching a satellite to explore the universe, and on the other side, a complex problem such as insecurity in a city. I'm not going to go through all the 10 properties that Rittel and Weber have discussed in their paper, but usually we recognize that we are in a wicked problem arena when we're struggling to define the problem that we are facing, to define it properly. Usually it's very difficult to find stopping rule to these challenges that we face. So, for instance, when do we stop thinking or working with environmental challenges? It's very difficult to say. And finally, some of these features that I selected for this session is that it's every action, it's a one go, and there is no trial and error. This means that what we are looking at is one-shot operations, like a policy, and it's very difficult to understand the counterfactual for this. So having tools and methods to deal with these features of our problems is critical to bring evidence-based solutions. So among these features that we face with complexity, here also again are a selection of some of the features that you might encounter in complexity. But one of these is heterogeneity of networks and its actors. So we usually face a diversity of actors that usually interact across scales, and they have different goals, might be proposing synergies, but also in conflict. And this is very clear for us in industrial ecology, this multiplicity of factors, for instance, a firm, a regional government, workers, and the international supply chain. This will make our understanding and our modeling a very difficult place to act. Moving on, we usually also face non-linearity systems, non-linear dynamics, which makes our calculations a bit more complex than pure mathematical optimization. In this sense, in circular economy or sharing economy, we usually think about rebound effects and these complex iterative tools where, for instance, adopting a circular behavior such as going to a second-hand shop we would think that it will promote lower material consumption, but actually, since it's cheaper, or I think I'm doing good, I go and I acquire more clothes than I would do if I would go for a first hand. So these are things that we need to take into consideration. Yeah, we don't see the image, but also emergence is another one. That's another property that we see. And here we usually find out some unexpected behaviors that come from the micro decision making, and we see the output at the macro scale. So industrial symbiosis networks are forming at the bottom up, and then overall at the system level, at the regional scale, we start to see how this system is changing. Usually also circular models emerge through collaboration, and these are things that are very difficult to model at a higher level. Finally, or one of the last one is path dependency. Also, our systems, our socio-economical systems are embedded within a higher framework, and these past decisions constrain our future options. So, for instance, if this is relevant to take into consideration when we're thinking about carbon-intensive infrastructures, way of doing business, and so on. Adaptation is one of other features that complexity problems arise and have, which is that actors will adjust their strategies and adopt different behaviors and technologies as the system evolves. So consumers will learn, let's say, to cheat the system or to avoid paying taxes. Consumers may adopt new design patterns or adopt a PV for their houses to improve their somehow utility. And finally, the last of these challenges is that these things happen on space, and this also pushes a complexity in terms of how things move across different scales, moving from residents to neighborhoods, to firms, to neighborhoods, regions, and so forth, even at the country level. And we know that this has an impact because things are related to each other the closer they are, and this can imply how the trust and knowledge of an economic sector evolves over time, or access to opportunities such as a recycling center or a second-hand shop. We believe that agent-based modeling it's a paradigm that allows us to take into consideration some of these complexities. And an agent-based model is a computer simulation where we try to bring to this model some rules to some extent, more detail or less detail about this complex to learn about this system in order to provide questions to our research questions or policy analysis. And having said that, researchers use this modeling mainly for, I would say, free frameworks or free ways of looking at these models. So one of them is really bringing generic knowledge about a topic. This is a keeping it simple model where we go for basic rules, a very minimal requirements. And then on the other side of this, in blue, we have a keep it descriptive type of modeling where we include as much context and reality as we can for the model to make it very context specific. And the argument of Lepage and Perroton is that there's another space for a type of modeling where we would like to use these sort of modeling tools as a learning tool to bring discussion, a co-creation between different actors. So I hope that you have a bit of freshness regarding the properties of agent-based modeling and complexity. And I would like to go back to WooClub and see which of these complexities that we have been discussing about, or if you have other sort of challenges, would be, what are the challenges and type of complexity that you face in your projects? And Casper, again, feel free to jump in when you start to see some activity in the WooClub. Can we see the others, Casper? Is it possible? Hitler groups. Thanks. Okay, it's quite interesting to see adaptation to be so high. It's an interesting property to incorporate into complex modeling. Yeah, but having said that, with this introduction, I will leave you to Casper and Ryu, that they will go into much more details about how to, what are the advantages of incorporating agent-based modeling into LCA. Casper, the floor is yours.
Thank you. If I'm correct, you can see now my presentation.
All good. Yeah, all good.
All
Great.
good.
So I'd like to start off with the practitioner. Practitioners that use LCA have various needs when it comes to assessing sustainability impact. They often find it difficult to navigate through the many approaches that are out there and align that approach with their goals and their scope of their LCA study. Scholars in previous studies already have described a wide range of applications and coined it as an alphabet soup of methods, which contains various soup flavors, so different types of LCA. And the literature is very extensive, but there is not so much literature on that systemizes these different flavors. And in our study, we propose to systemize the flavors of LCA based on defining aspects of LCI modeling. And we do so because life cycle inventory stage is the backbone of every LCA study. By studying the LCI characteristics and using the notion of these LCA soup flavors, we were able to find 4 defining aspects of LCI modeling, and those are dynamicity, temporality, scale, and causality. And in the next slides, we will discuss these defining aspects of LCI, and also how ABLCA can contribute to furthering understanding these aspects. So dynamicity refers to how a system modeled in the LCA changes over time, and temporality refers to the point in time that the LCA represents, or also the LCI in the model represents, or aims to represent. For example, retrospective models versus forward-looking models. Many LCA models are static models. They do not contain any time dimension, and results represent a snapshot and aggregated view. They assume fixed conditions over the entire life cycle, and they mostly use average values for emissions, energy, and impacts. Often, these static models can be very convenient. For example, when you want to make a simple comparison between two product systems. However, steady state models are also criticized because they neglect important environmental impacts that can only be observed when adopting a dynamic perspective. Examples include changes in supply chains or market dynamics influencing the technosphere, and also, as mentioned by you earlier in our WOOC lab session, rebound effects due to varying vintages of energy efficient products. Dynamic LCA models are already out there, and they can track impacts per phase or time period, for example, year by year. And forward-looking approaches such as prospective LCA enable the user to provide decision-making support for the future. All these studies show that incorporating dynamicity and temporality is far from straightforward, and it requires methods that go beyond mainstream analytical techniques. For example, you need some graph traversal algorithms and to incorporate scenario thinking. So when you use agent-based modeling to extend your LCA study, ABLCA, you can yield dynamic models in forward-looking LCA. Because agent-based models are dynamic by default. They include always the dynamic and temporal aspects. Yeah, you can study, as mentioned by Jonathan, the emergence, path dependency, and adaptation mechanisms. Our colleague Paul Carey at INRAE did a structured review of scientific literature focusing on case studies using ABLCA, and he looked at papers between 2019 and 25, yeah, after excluding duplicates, he found 33 studies that were really relevant for this topic. And the results show that 58% of those ABLCA studies were future-oriented, and 21% were yeah, trying to model current contexts. He also found that granularity, so the simulation steps, are very important part, and also the simulation duration, and they need to be aligned with the goal and scope of the studies. But granularity can be a very challenging task, can be very challenging due to data availability issues. ABLCA can nevertheless still yield yeah, a lot of results in forward-looking LCA and in insights in dynamicity and temporality. The next aspect is scale, and scale refers to the extent of the target system which is under study. LCA was originally developed as a spatially and temporally independent approach, for example, to compare product level assessments. The product-based scale was subsequently expanded to assess the sustainability impacts at the level where decisions are being made, organization level, and later, because there was a need for comprehensive environmental assessment, also on a larger scale, um, tracking economic activities throughout production consumption systems. On territorial levels, also territorial LCA was developed. And territorial LCA evaluates all production and consumption within a territory, integrating GIS tools for land use planning. And it is often applied in agriculture or urban mobility and waste management. And what can be done, it shows how decisions at the territorial level are being made. However, it does not connect the dots between small scale decisions and that are also very location dependent, for example, eutrophication. And this is often needed to also include that. So when it comes to agent-based LCA, you can enable multi-scale analysis, and you can include those location-sensitive examples, and also specify spatially explicit conditions, integrating agents' decisions that could generate spatially explicit impacts that could also be accounted for to inform territorial planners. Still, agent-based LCA does not eliminate the need for allocation methods, so there's still some work to be done, but it can help bridge the gap between the multiple scales and also the gap between individual behavior and system behavior. So it's essentially bridging scales and also including individual behaviors. So the next aspect that we're going to discuss is causality. Many practitioners are interested in information on environmental burdens that occur directly or indirectly as a consequence of a decision. Consequential LCA was developed to meet this need, and many consequential LCA studies requires the LCI model to include activities and flows expected to change with variations in demand for the functional unit. But more recently, this definition was expanded by Schaubroek by clarifying that consequential LCA seeks to incorporate impact-associated causes in time and context, excluding other plausible causes. Consequential LCA goes beyond biophysical and technological causality by incorporating economic causality. And it often relies on other types of modeling, such as economic equilibrium models, technology choice models, and system dynamics. And these types of CLCA assume economic rationality in an aggregated manner. Constructing a fully causal LCI model is, however, very difficult, also due to gaps in data availability and the feasibility issue of modeling complex processes. Therefore, instead of a binary label, some studies suggest to describe LCI models along a degree of causality, from less causal to more causal. ABMs are also already used in consequential LCA. As shown by some scholars, ABMs make it possible to model more nuanced, dynamic, heterogeneous, and interaction human behaviors. For example, you can incorporate social networks, habituation, environmental motivation, and diverse cognitive processes. The feasibility of modeling policies is often fundamentally restricted by the structure of the model, but ABMs allows us to experiment at different levels of scale, and is therefore able to capture more nuanced human behaviors, but also include more multi-level interventions. So in essence, ABM facilitates modeling a wider range of interventions and including human behaviors, and therefore it expands policy analysis in LCA beyond technological and economic changes, encompassing other drivers of decision making. So to wrap it up, in our work, we present the 4 aspects of LCI modeling in a diagram, which is shown here. You can see that these flavors can be mapped in the diagram. For example, study A here refers to an attributional dynamic LCA focusing on a product. And study C refers to a territorial LCA using GIS data to analyze a region. So the axes represent dynamicity, causality, and temporality, and the scale is shown by the size of the sphere. In essence, ABMs combined with LCA are not restricted to one or a few of these flavors, and the aspects can be aligned according to the LCA goal and scope. So ABLCA allows studies to combine all 4 flavors if needed, but they can also be taking a few of those flavors. I'll wrap it up here, and we can go to Dr. Riu Koiden now to continue this presentation and elaborate on how ABLCA offers a more holistic paradigm.
All right. I hope you can hear me.
Yep, all good.
Yep.
Okay. I need to spot myself here. Okay. So, and thanks, as Casper presented, there's lots of contribution of ABM on LCA, but what does it mean for industrial ecology research? We believe that the complexity science approach can bring paradigm shift to industrial ecology research. So from here, I'm going to further explain the 3 perspectives, which is socio-technical systems and policy modeling, and then deeper uncertainty. So the first point is about going beyond technological and economic causality. As you know, industrial ecology mainly focusing on materials and energy flows and human activities' impacts on the environment. So it's mainly about in the middle here. But ultimately, you know that what we are looking at is embedded in a much broader socio-technical ecological system, even including governments, NGOs, and political system, and consumer behaviors, and also interaction with technology production layers and environmental layer. When we are aiming at systemic transformations, it requires to investigate behavior shift and overcoming inertia of socio-technical systems, but LC studies mostly rely on technocratic assumptions. So our initiative colleague Paul Curry did a review of agent-based LCA studies, and he found that 64% focusing on technological scenarios, but that's dominant. But still, this agent-based approach can bring these institutional scenarios and behavioral scenarios to large extent. So this is the area we have to explore more. But an issue is that we have to find realistic way forward because modeling behavior and decision-making process and link it to LCI modeling is not easy, and complete agent-based digital twin is not practically feasible. So as practitioner, researchers, we have to selectively decide which elements should be modeled using agent-based approach and depending on research objectives, available resources, and also our own judgment. So I think this is also to answer to Daniela's question in the comment that bringing system dynamics into this agent-based and LCA is also addressing this, maybe because it's also good to model using system dynamics as part of the system, because everything to be represented by ABM is more hard. And for example, for technological optimization like sustainable feedstock for energy production, well, it's fine to emphasize physical causality using conventional LCA approach. But for example, for designing socio-technical systems like circular business models, mobility sharing service, industrial symbiosis, we may need to model bidirectional influence of consumers and demand-side behaviors on the value chain, which is needed. And the second point is about endogenizing policy interventions or policy modeling. As you know, industrial ecology is meant to be policy relevant, but we also know that we have limited toolkit to model policy intervention themselves. So here's a comparison of conventional LCA models and agent-based approach. So how to represent policy in LCI models is to make a direct changes in the technology matrix or demand vectors. But in agent-based LCA, we can have environmental parameters that are going to change the influence the agent behaviors. So it's not directly change the physical flow, but it goes through decision makers changes, so changing decision making of agents. And how does it influence actor decision? In conventional LCA model, it is assumed but not explicitly models. But in agent-based approach, we can endogenize actors' response to of the policies to capture system-wide consequences. So what policy instruments are suitable in these different types of models? For conventional approach, of course, technological improvement, it fits with it. And perhaps regulatory instrument also can fit, and also economic instrument in case of consequential LCA approach. But beyond that, for example, information-based instruments or the combination of different economic, regulatory, and other policy mixes, that is a bit difficult in conventional approach, and that's where agent-based LCA approach is promising. So agent-based modeling has been increasingly recognized for simulating policy intervention to support policy making, and it can enable virtual what-if experiments, for example, policy design, and also ex post evaluation. And the power is that we can consider how actors perceive, adopt, or resist change, so which is influential factors of policy interventions and effectiveness. So that's why agent-based LCA approach is suitable for modeling variety of instruments and their impact on life cycle environmental impact, and also to explore positive or negative synergy of policy mixes. And the third point is about deep uncertainty. According to the literature, there are three types of uncertainty. One is about probability distribution of key parameters. For example, variability in LCI data, uncertainty in background data, and sustainability impact factors. We are addressing it through sensitivity analysis in a conventional way. But uncertainty is not just about parameter, but also structure or conceptual models describing system interactions. So basically in conventional LCI, we are assuming a fixed linear algebraic model structure. But in agent-based approach, we could have various possibility of model structure like agent decision. If you have system dynamics incorporated, it's also like feedback loop. And that itself, if we incorporate going beyond conventional LCI to agent-based approach itself, it's also to explore this difference in conceptual models. And because the 100% accurate modeling is not possible, there's also uncertainty in the choice of this modeling structure. So that's why we could also utilize the sensitivity analysis, focus on model structure, but not only parameters. And the third is how to assess the desirability of outcomes. So the desirability of outcomes could differ among stakeholders. This is like different aspect of values by people, and also may change over time. But mainstream LCA tend to ignore this perspective. In ABM, we could have broader indicators than environmental impact, like economic, social, and behavior indicators. So here, the possible use of agent-based LCA is that we can represent stakeholder behavior, that could be consumers, producers, by modeling them as agents, and then simulate the future changes of these outcomes, environmental and other aspects. And also in a participatory approach, incorporated, we can discuss their desirability with stakeholders. And also to find solution spaces, which policies are effective, what uncertainty factors are important, and to see where most agents are in the desired situation in the model. And that kind of more advanced technique to address this diverse set of uncertainty could be possible in agent-based LCA approach. So based on this understanding, we'd like to propose these recommendations for agent-based LCA researchers and practitioners. So first is to clarify why are we using this agent-based approach. So you can answer these guiding questions along with the 4 aspects presented by Caspel. In terms of temporality, are you looking at prospectively or retrospectively? In terms of dynamicity, does the system change dynamically? Does the impact dynamic or static? In terms of scale, are you interested in the per product impact, territorial impact, or organizations or household-wide impact? In terms of causality, is the techno-economic causality enough? Or that social agent play roles or not? And the second is to clarify how. And there is already existing taxonomy of integration techniques. For example, in terms of direction of change, of course, the ABM may modify foreground of LCA model, but also does it influence the background models? Or also like does LCA provide feedback to ABM or not? And also in terms of integration method, does soft or tight coupling enough, or do we need hard coupling, or sometimes we could also do surrogate or meta modeling? And also which software platform you're using, are they different between LCA and ABM, and how we can couple them, or we can maybe use the single platform to do both. And also to clarify which system you're focusing on. For example, if the system includes more complexity, then you may need more causal and consequential modeling approach, so you could have more roles of agent-based modeling. And also function unit in this agent-based LCA is a bit argumentative thing because it ultimately depends on a point of observation. So ABM is quite flexible. So one possibility that we could have multiple function units in ABM to be used, or other possibility that we could have more neutral function unit, like instead of per product, we could have like per community or per country or per certain number of household environmental impact to be quantified. And also to clarify which interventions, are they technology change or economic, social, information-based instrument? If you have more focus on behavior and social aspect, then you could have more central roles of agent-based modeling. And then finally, how uncertain? Uncertainty is not only about parameters, but also model structure. Then we could consider sensitivity analysis of model structures. That's also been done in agent-based modeling or computational simulation community. And also about deep uncertainty, we can also learn from this decision-making under deep uncertainty or DMDU community. They have a lot of literature and also guidance, but we still haven't really addressed that in this LCA and agent-based modeling community. So that's it from my side, and thank you so much.
Thank you very much, Ryu. Thank you for the presentation. And well, in today's session, we have seen how what is complexity and why do we care about it. Then Casper explained a little bit of why agent-based modeling can be beneficial for LCI modeling, considering the different aspects. And finally, Ryu discussed and provide some recommendations for coupling agent-based modeling and lifecycle assessment. So I see some questions in the chat. Those are very, very nice questions. Maybe we'd like to discuss them after finishing the final block of the interaction. So Kaspa, I invite you to share your screen again and to go to the final block of the interactive session. And then we can jump to some questions from the audience. Hopefully we can manage with the time.
Yes. So here is the next question on WooClap. So please join us again. So here are here's a list of benefits that ABM can bring for advancing LCA. And if you are interested in it, which benefits would be most interesting for you? So we have dynamicity, temporality, dynamic modeling, forward-looking modeling, economic causality or social and behavioral causality, scales, also georeferencing, holistic systemic change, policy modeling, deep uncertainty. But also if you have other interests that come up in your mind, you can vote on that and specify. Key mechanisms like rebound mechanisms. That's a topic that is coming back more often. So dynamic modeling is very popular in the votes, but also social and behavioral causality. And then policy modeling and holistic system change. So for time reasons, I think it's wise to go to the next question, right? So please wrap it up for the last few seconds. And I will go to the next question. Yes. So our question is, what is needed for you to incorporate ABLC in your work? So you can think of anything, knowledge, skills, or fill out everything you like. A good modeling team, yes. Robust data, yes, that's of course very important. Modeling guidance, transparency. Yeah, so it's very important to explain the model in a transparent way to make sure that it can be replicated if needed, or making the model, yes. Methodological questions, but also data questions about robust data are the most important. A suitable tool, that's also interesting. Or a tool suite. Software compatibility. It's also very practical issues. Okay. So please finalize your last inputs so we can go to the last question. Yes. And we go to the last question. So what next steps should be taken to advance ABLCA as a community? So the previous question was more about what do you need, but this question is about what steps can we take as a community to make this happen. And perhaps looking at the time, perhaps it would also be nice to address some questions in the chat. Can you take it over for me again? Let's look at.
Yes, there are several questions in the chat. Some of them are being answered by other people in the audience. But there was the first one that was already answered, but I believe Rio asking about integrating ABM with system dynamics. And there's one that says, I would like to discuss later why do you claim that agent-based digital twin is not feasible? And I believe that goes to Rio's presentation.
Well, I mean, it's not really like we're not claiming that it's ultimately not unfeasible, but at this moment it's quite difficult to represent everything and in AVM, and also digital twin needs all the real-time flow of information, and that these data is not yet available. For example, when it comes to for example, circular economy, it's not yet that all the real-time data is available. But I think those things we can also learn from the development in the social simulation and digital twin community, and we should also catch up with the development there.
Okay, thank you, Ryu. There's also a couple of very interesting questions, and they are from Michael Sogard. The first one says, I'm afraid that ABM just increased the belief that you can model socio-technical changes. I do not see socio-technical system approaches in your ABM approach. Yeah, that's the first one. And the second one is also saying that I'm afraid that ABM, by claiming that integrates more dimension, makes the analysis and the transparency even smaller than in classical life cycle assessment. Okay, so we'd like to address to that, Rio, as well.
Okay. I think I want to address first with the maybe more later one, that the ABM just reinforced the classical problem of LCA, where researchers believe that LCA gives the right result and not yet the LCA result as an aspect of stakeholder dialogues. I think all the questions related to this. So the result of ABM and also how we use ABM or AB-LCA approach, we should ultimately use it in a participatory way as well. So that's like we have to be transparent about how we model and what data we are using and what are the limitations of the models, and also better to invite stakeholders or decision makers and involve them, and ultimately it's so that's why we're calling as paradigm shift, because it's not agent-based model. What we can do, it's not just about very precise predictions, but the power is that we can explore quite a broad wide range of scenario. Could be like thousands or tens of thousands of different scenarios, which is ultimately quite uncertain, and that's something we also need to communicate. We also need to find a way to better communicate to stakeholder decision makers about the result of LCA, and that paradigm is, I would say, quite different from more conventional LCA paradigm, like to try to say this is more accurate result and then do some sensitivity analysis of uncertainty. But I think those things, it's quite exciting, but we have to discuss further with the subsequent event of the initiative.
I do agree, and I believe that going back to the comment about more dimensions make the transparency even smaller. It's important to understand that agent-based modeling is not the only way of modeling a system. And indeed, that's what Rio presented in his table, where he showed, depending on the type of causality you want to represent, a conventional analytical LCA could be enough. And it seems to me that agent-based modeling is the right tool to explore and to analyze and to try to understand explicitly how certain events are happening. And differently from how we interpret sometimes LCA results, because we have an aggregated number, in agent-based modeling, we have the chance to audit how this number is calculated and again put our assumptions to challenge. And this addresses as well a comment from one other member of the audience. I believe it was referring to let me find it. I think I lost it. Assumptions, yes. How do we ensure as much possible that that we model actual behavior and not solely predicted behavior based on our assumptions? A lot of agent-based models rely on empirical data, which indeed come from interviews and attempt to represent real behaviors. Something that is more difficult to validate indeed is emergence. Behaviors can be explicitly described in models. You program them, you explain, they can be audited, challenged if necessary. But emergence is indeed something difficult to validate sometimes, because emergence is the reason why it's not so easy to model certain system outcomes with conventional analytical tools in a bottom-up approach. But I believe that indeed depends on what kind of behavioral models you use or assumptions. And as long as you make them explicit, they are audited. They can be audited. So I think that it's a +1 for transparency. So there's another question about to what extent can agent-based modeling be used to anticipate behavior later. Oh, okay, yeah. Okay, to what extent can agent-based model be used to anticipate behavior ex ante before the implementation of interventions? Do you want to answer?
Oh, sorry, are you asking me or?
Any one of you. You're free to.
I can react to that. So it's also a bit related to what is mentioned earlier. So yes, it can be done as long as you really stay connected to reality, and that is mostly done by participatory way of modeling. And making sure that the mechanisms in the model are well understood by everyone, and also agreed upon whether this is close enough to reality.
Thank you very much. I appreciate the engagement and the questions. This very challenging questions indeed are the reason why in the initiative we are opening the floor for this kind of discussions. And indeed, our objective is to improve the methods we use, improve the approaches we have, and of course, you are invited. Please, Casper, could you share the slide of just to remind everybody about our working session, and then I can close up the event. So thank you to all the presenters, and thank you for the audience for staying until this long. I know that some of you already left, and I appreciate a lot the questions. I apologize if we couldn't manage to answer all of them, but I invite you to join the working session that we're going to have on December 5th, 10 a.m. And it's open to everybody. We want to have your opinions, your thoughts, and if you want to contact us, you can do it through the email, complexitylca@gmail.com, or visit the website, complexitylca.github.io. Thank you very much to all, and I invite you to continue in the Industrial Ecology Day and join the other sessions. This session will be recorded, and you probably will receive the video via email. So thank you very much, and have a nice day. Thank you very much. Thank you to all.